You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Reliability patterns are a collection of structured techniques designed to ensure that artificial intelligence systems and their surrounding components act in consistent, dependable ways, even under imperfect conditions. When people interact with technology, whether through an AI chatbot, an automated assistant, or a large-scale business pipeline, they expect a degree of predictability. They want to feel confident that pressing a button, submitting a query, or retrying an action will not cause confusion or chaos. Reliability patterns meet this need by shaping the behavior of AI systems, so they fail gracefully, recover smoothly, and provide consistent outputs. They do not guarantee perfection. I will always have elements of variability, but they ensure that variability is managed within predictable boundaries. By framing these patterns as design recipes, engineers can draw from a body of shared knowledge rather than improvising under pressure. This shared vocabulary improves collaboration, reduces risks, and strengthens the overall resilience of AI deployments. The importance of reliability in artificial intelligence cannot be overstated. People do not adopt systems they cannot trust. Imagine if an online banking assistant answered your balance inquiry differently each time you asked, or worse, became unresponsive halfway through the interaction. Such behavior would immediately undermine confidence, regardless of how sophisticated the underlying model might be. For individuals, unreliability creates frustration. For businesses, it creates tangible financial loss and potential regulatory trouble. Reliability is the bridge between technological capability and real-world adoption. Many AI systems can demonstrate impressive capabilities in research settings, but without reliability, they stumble when introduced to production environments. Reliability ensures continuity, predictability, and user satisfaction. It is what allows AI to move from experimental novelty into essential infrastructure, just as the reliability of electricity transformed it from an unpredictable curiosity into the backbone of modern civilization. One of the simplest but most effective patterns for reliability is the timeout. A timeout establishes a maximum period that the system will wait for a response before moving on. To use a home analogy, think of boiling pasta. You set a timer because you know there is a reasonable expectation for how long the water will take to boil. If it hasn't boiled after the timer rings, you assume something is wrong and stop waiting. Similarly, in computing, if a process takes longer than a reasonable threshold, the timeout aborts it. This prevents the system from hanging indefinitely and frees resources for other operations. Timeouts acknowledge the reality that not all processes complete as expected. Rather than letting delays propagate, they cut off the problem early. By enforcing limits, they turn uncertainty into predictability. Users may not always get a perfect answer, but they will not be left waiting indefinitely, which is often worse than an incomplete result. The use cases for timeouts are diverse. In real-time chat applications, if a large language model does not return an answer within a set number of seconds, the system can present an alternative message such as, "I'm sorry, I'm having trouble right now, please try again." This fallback response is better than silence, which leaves the user guessing. In multi-step business processes, timeouts prevent a single, slow component from holding up the entire workflow. For instance, if an AI-powered fraud detection system cannot analyze a transaction within a fraction of a second, the system may flag it for manual review rather than holding up all customer payments. This ensures continuity, even if some results must be deferred. Timeouts balance responsiveness with completeness, and designers can tune them carefully. Too short, and they disrupt valid processes. Too long, and they create bottlenecks. Finding the sweet spot is both art and science, requiring testing and observation. Another essential reliability principle is idempotency. Though it may sound complex, idempotency simply means that repeating an operation produces the same result as doing it once. A clear analogy is pressing the elevator button. Whether you press it once or a dozen times, it still only calls one elevator. In computing, this principle ensures that if a system retries a request due to a failure, the outcome is consistent and does not multiply effects. Idempotency protects against unintended duplication, corruption, or runaway side effects. It is particularly valuable in AI systems, where retries are often necessary because of temporary network errors or delays in external services. Without idempotency, each retry might create additional unpredictable consequences. With it, retries are safe, and recovery becomes straightforward. Idempotency turns the risk of repeating actions into a strength, ensuring continuity without compounding mistakes. The benefits of idempotency become especially visible in transactional environments. Consider an AI travel assistant booking flights. If the booking process fails midway and the system retries, without idempotency, the user could end up with multiple tickets, each charged separately. With idempotency in place, the system recognizes that the transaction has already been completed and prevents duplication. In other domains like healthcare, idempotency ensures that patient records are updated once, not multiple times, even if a process is retried. For financial systems, it prevents duplicate transfers, avoiding both confusion and loss. By implementing idempotency, developers make systems not only more reliable, but also more trustworthy. Users know that errors will not be magnified, and organizations know that recovery processes will not cause additional damage. Another pattern unique to AI is transactional prompting. Traditional software systems use transactions to ensure that actions either succeed completely or fail clearly, never leaving the system in a half-finished state. Transactional prompting applies this same principle to interactions with language models. The idea is to craft prompts in ways that encourage outputs that are atomic, predictable, and easy to validate. For example, asking for structured data in JSON format with all fields present creates a clear success criterion. If the model provides all fields, the output is accepted. If it does not, the system recognizes the failure and retries. This approach avoids ambiguous or partial outputs that could confuse downstream processes. Transactional prompting essentially turns the inherently probabilistic nature of AI into something that behaves more like a traditional transaction, with clear boundaries between success and failure. Examples of transactional prompts illustrate how powerful this idea can be. Instead of simply asking, "List some benefits of renewable energy," a transactional prompt would specify, "Provide exactly 3 benefits of renewable energy, each labeled numerically 1 through 3, and nothing else." This clear structure allows the system to validate the output easily. If only 2 benefits appear, or if additional text sneaks in, the system can flag the response as incomplete and request a retry. The reliability comes not from assuming the AI will always behave perfectly, but from designing prompts that make validation possible. This structure transforms outputs from vague text into predictable data, bridging the gap between flexible language generation and rigid system requirements. Fallback mechanisms represent another reliability safeguard. A fallback is essentially a backup plan that the system uses when the primary method fails. The concept is familiar in everyday life. Carrying a spare tire in your car is a fallback in case of a flat. In AI, fallbacks might mean switching from a large, slow model to a smaller, faster one when response times exceed limits, or returning cached information when live services are unavailable. The goal is not perfection, but continuity. A system with fallbacks ensures that users are never left stranded. Even if the highest quality response is unavailable, the user still receives something useful. This preserves trust, because most people can tolerate reduced quality more easily than complete failure. Monitoring is another cornerstone of reliability. Even with timeouts, idempotency, transactional prompting, and fallbacks in place, systems will still experience failures. The question is whether those failures are detected early or allowed to escalate. Monitoring provides visibility. Logs, dashboards, and alerting systems act like the gauges on a car dashboard, showing when something is out of range. They allow engineers to see when timeouts are being triggered too often, when fallbacks are engaging, or when transactional prompts are failing validation. With this information, teams can respond quickly, fix problems, and refine thresholds. Monitoring transforms failures from hidden surprises into manageable events. It also provides valuable feedback for improving reliability over time. As AI systems scale, reliability patterns become not just important but essential. In small experiments, occasional inconsistencies might be tolerable, but at enterprise scale, with thousands or millions of transactions, even rare errors accumulate into major issues. A 1% error rate might seem small, but across millions of interactions, it becomes catastrophic. Reliability patterns prevent these small cracks from expanding under the weight of scale. They ensure that systems grow in capability without collapsing under complexity. Without reliability, scaling amplifies fragility. With it, scaling becomes sustainable and safe. This distinction is what separates systems that remain experimental curiosities from those that evolve into enterprise-grade infrastructure. Reliability is especially critical in regulated industries, where unpredictable behavior is not an option. Banks, insurers, and healthcare providers cannot afford systems that give inconsistent answers or duplicate operations. A compliance chatbot that sometimes provides one interpretation of policy and sometimes another is not just confusing, it could be legally dangerous. Reliability patterns provide the predictability needed to operate within regulatory frameworks. They ensure that outputs are consistent, failures are controlled, and recovery processes do not introduce new risks. By embedding these patterns, organizations demonstrate both technical competence and regulatory responsibility, building confidence with both users and oversight bodies. Testing reliability is as important as designing it. Systems cannot simply be trusted to perform, they must be proven. Stress testing subjects systems to heavy loads to ensure that timeouts, fallbacks, and retries function correctly. Chaos engineering goes a step further by deliberately introducing failures into live systems to observe how they recover. These practices may sound counterintuitive. Why break something intentionally? But they reveal weaknesses before they become real problems. By practicing failure in controlled conditions, teams build confidence that their systems can survive the unexpected. Testing transforms reliability from a theoretical goal into a demonstrated capability. When viewed together, these reliability patterns form a layered defense against unpredictability. Timeouts cut off unresponsive processes. Idempotency ensures retries are safe. Transactional prompting enforces structured outputs. Fallbacks maintain continuity. Monitoring catches failures early. Testing proves resilience. No single pattern is enough on its own, but together they form a comprehensive framework. Like overlapping safety nets beneath a trapeze artist, they ensure that even when one net is missed, another is ready to catch. This layered approach is what allows AI systems to operate not just impressively but reliably, earning the trust required for wide adoption. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Retries are one of the most common tools for dealing with transient failures, but they only work safely when paired with ID impotency. Without ID impotency, each retry risks multiplying effects, creating duplicate actions or unintended consequences. Imagine refreshing a web page during an online checkout. If the underlying system lacks ID impotency, each refresh could generate a new order, resulting in multiple charges. With ID impotency, the system recognizes the repeated request as the same action and ensures that it only executes once. This pairing makes retries not only safe but also powerful, because it allows systems to recover automatically from temporary issues without introducing new errors. In the context of AI, retries might mean resending a query to a model that initially timed out. With ID impedancy, the response integrates seamlessly into the workflow without duplication. This relationship demonstrates how reliability patterns are often strongest when used in combination rather than isolation. Partial failures are another important consideration in reliability design. In complex AI systems, especially those operating across multiple services, it is common for one component to fail while others succeed. Without careful design, this can lead to cascading problems where an entire pipeline collapses due to a single error. Reliability patterns prepare for partial failures by isolating issues and allowing unaffected parts of the system to continue functioning. For example, if a recommendation engine cannot retrieve one category of results, it might still display results from other categories, with a note indicating that some data is temporarily unavailable. This approach mirrors redundancy in the human body. If one eye is obstructed, the other continues to provide vision. By acknowledging that partial failures are inevitable, designers can create systems that degrade gracefully, rather than collapsing entirely when something goes wrong. Circuit breakers provide another safeguard by controlling interactions with components that are repeatedly failing. Borrowed from electrical engineering, the idea of a circuit breaker in software is to stop sending requests to a service that has failed too many times within a short period. Continuing to send requests wastes resources and risks, destabilizing the broader system. In AI workflows, a circuit breaker might prevent repeated calls to an external database that is currently offline, redirecting queries to cached responses instead. This allows the system to conserve resources, protect the user experience, and avoid compounding errors. When the failing service recovers, the circuit breaker resets, allowing normal operation to resume. This pattern illustrates how reliability is not only about surviving individual errors but also about managing repeated, systemic failures in a controlled way. Graceful degradation is another principle that enhances reliability. The goal here is to ensure that when a system cannot provide its full functionality, it still delivers something useful rather than failing completely. In AI systems, graceful degradation might mean providing a simplified answer or fallback explanation when the primary model is unavailable. For example, a speech recognition system might degrade from full transcription to simple keyword spotting if resources are constrained. A chatbot might fall back to scripted responses if the generative engine times out. These fallbacks are not ideal, but they preserve continuity and maintain a baseline of functionality. The human analogy is a restaurant substituting ingredients when one item is out of stock. Customers may not get exactly what they ordered, but they leave fed rather than hungry. Graceful degradation sustains trust by ensuring that failure never results in complete emptiness. Transactional integrity extends the reliability of AI systems by enforcing all-or-nothing outcomes. This means outputs must either succeed in full or fail clearly, without leaving ambiguous partial results. In finance, this principle prevents situations where money is deducted from one account but not deposited into another. In AI, transactional integrity might prevent a system from returning a partially formatted JSON object that could confuse downstream services. Instead, the system either delivers the full, correct structure or signals a failure that triggers a retry. This clarity is vital for predictable operation. Ambiguity creates risks because it leaves both humans and machines uncertain about what really happened. By designing AI interactions to behave transactionally, engineers ensure that errors are detected early and corrected, rather than silently propagating through the system. Prompt validation provides an additional safeguard against malformed outputs. Even with carefully designed prompts, AI systems may still produce unexpected results. Validation checks the output against defined criteria before passing it downstream. For example, if a model is asked to produce 3 numbered items, validation ensures that 3 distinct items are present. If not, the system rejects the output and requests a retry. This is analogous to a teacher grading an assignment. If the student answered only 4 of 5 questions, the missing answer is flagged. Validation prevents errors from spreading by catching them early. It transforms AI outputs from loosely structured text into predictable data that other systems can rely on. By combining prompt design with validation, developers create a feedback loop that continually reinforces reliability. Redundancy is another cornerstone of reliability engineering. The principle is simple: never rely on a single point of failure. In AI systems, redundancy can mean running multiple models in parallel and using whichever produces a valid response first. It can also mean duplicating servers, storage systems, or network paths so that if one fails, others can take over. This mirrors practices in aviation, where critical systems have multiple backups to ensure safety. Redundancy ensures availability and continuity even when individual components fail. It also provides resilience against unpredictable conditions. While redundancy increases costs, it provides peace of mind by ensuring that no single malfunction can bring down the entire system. For AI applications that support critical business processes, redundancy is not a luxury but a necessity. Balancing latency and reliability is one of the recurring challenges in system design. Reliability patterns often add extra steps such as retries, validations, or redundancy, which can slow response times. For users, especially in interactive applications, speed is important. Too much delay can undermine the value of the system even if it is reliable. Designers must weigh these trade-offs carefully. In life-critical contexts such as healthcare or aviation, reliability outweighs speed. In casual applications like entertainment chatbots, users may prefer faster answers even if occasional errors occur. Some systems offer configurable modes, allowing users to prioritize either speed or reliability depending on their context. By making these trade-offs explicit, designers ensure that reliability measures enhance rather than diminish the overall experience. Reliability also contributes to system security. Unreliable systems are often easier to exploit because they behave inconsistently under stress. Attackers can use these inconsistencies to discover vulnerabilities or trigger unintended behaviors. For example, if retries are not idempotent, attackers might deliberately force retries to cause duplicate actions. By enforcing predictable patterns, reliability safeguards close off avenues for exploitation. They reduce the system's attack surface and make it harder for adversaries to manipulate outcomes. In this sense, reliability is not just about user experience or performance, it is also a form of defense. Secure systems are reliable systems, and reliable systems are more secure because they leave less room for uncertainty to be weaponized. Cost implications are another dimension of reliability. Many reliability measures, such as retries, redundancy, or monitoring, consume additional resources. They increase compute cycles, storage, and maintenance overhead. On the surface, this might seem inefficient. However, the true cost of unreliability is far greater. Outages, duplicated actions, or corrupted results can lead to financial loss, reputational damage, and regulatory penalties. Reliability investments function like insurance. They add a predictable cost up front in exchange for protection against catastrophic failure. Organizations that cut corners on reliability may save in the short term, but risk devastating consequences later. By contrast, organizations that invest in reliability build long-term sustainability and resilience. The trade-off is clear. A modest increase in operating cost prevents far larger losses down the road. From the user's perspective, reliability patterns create a seamless, dependable experience. Most users never see the retries, validations, or fallbacks happening behind the scenes. They simply experience a system that responds consistently, does not hang indefinitely, and rarely produces confusing results. This invisibility is the mark of successful reliability engineering. Like electricity or running water, reliability is noticed most when it is absent. Users quickly abandon systems that feel unreliable, but they rarely comment on reliability when it works well. By prioritizing reliability, developers create user trust, and trust fuels adoption. Once people trust a system, they rely on it more heavily, integrating it into their daily routines or business operations. This virtuous cycle strengthens the role of AI in society. Industry case studies show reliability in action. In customer service bots, ID impotency ensures that repeating a request does not generate duplicate support tickets. In compliance systems, transactional prompting ensures that answers always match regulatory templates, avoiding ambiguous interpretations. In healthcare applications, redundancy guarantees that decision support remains available even if one model crashes. These examples demonstrate that reliability is not theoretical. It is actively applied in high-stakes domains. Each case shows how reliability transforms AI from a novelty into a dependable partner. Organizations that adopt these practices not only reduce risks but also unlock greater value from their AI investments, because dependable systems can be trusted with more critical responsibilities. Research into reliability continues to evolve. Emerging techniques such as consistency-enforcing decoders aim to make AI outputs less variable by design. Other approaches focus on self-validation, where models check their own outputs before releasing them. These methods show that reliability is not just about wrapping safeguards around AI systems. It is also about improving the core models themselves. By combining reliability research with engineering patterns, the future of AI may include systems that are reliable at both the output and the architectural levels. This convergence represents an exciting frontier, one that promises to make AI systems even more robust and trustworthy. Looking ahead, reliability will remain central to enterprise adoption of AI. As organizations integrate AI into mission-critical workflows, they cannot afford unpredictability. Reliability patterns will be embedded from the start, not added as an afterthought. Just as no one would build a bridge without considering safety redundancies, no one will deploy enterprise AI without reliability safeguards. These patterns will define the difference between AI as a novelty and AI as infrastructure. They will ensure that systems are not only powerful, but also predictable, trustworthy, and safe. Reliability is not just a technical requirement. It is the foundation for AI's role in the future of work and society. Memory systems provide a natural complement to reliability by sustaining context across interactions. Reliability ensures that outputs are consistent in the moment, while memory ensures that consistency extends across time. Together, they allow AI systems to support complex, multi-step workflows without losing track or producing contradictory responses. Just as reliability prevents failures from destabilizing single interactions, memory prevents fragmentation across repeated ones. In the next episode, we will explore how memory systems reinforce reliability and open the door to more advanced, context-aware AI experiences. This episode has explored the critical role of reliability patterns in making AI systems trustworthy and resilient. We began with the importance of reliability as the foundation of user trust, then examined key patterns including timeouts, ID impotency, transactional prompting, fallbacks, monitoring, and testing. We extended this discussion into advanced practices such as circuit breakers, graceful degradation, prompt validation, redundancy, and consistency enforcing research. Throughout, we emphasized that reliability is not achieved through a single technique, but through a layered combination of safeguards. These patterns ensure that AI systems fail gracefully, recover predictably, and scale sustainably. They protect users, safeguard organizations, and strengthen security by reducing uncertainty. Most importantly, they transform AI from an impressive but fragile tool into a dependable partner. As AI becomes embedded in critical business and social functions, reliability will remain the non-negotiable foundation for trust and adoption. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.